Okay, hi everyone. Thanks for coming to another Graphs and Matroid seminar. Today we've got Jagdeep Singh from LSU, who's going to be talking about two-cographs and binary cometroids. Go ahead, Jagdeep.
Thanks, Sheila. I will be talking about two-cographs and binary comatroids. Now, a disclaimer, this has nothing to do with matroid duality, and this is joint work with James Oxley. Okay, so let's start with this well-known class of graphs called cographs. There are lots and lots of ways of describing cographs, and we'll start with the recursive one. And they can be defined as the graphs which are generated from the single vertex graph K1 using the operations of complementation and zero sums. Okay, so one might ask, what are examples of such graphs? Well, complete graphs. And how do you get complete graphs? Well, if you have K1, just take disjoint copies of K1, you get a bunch of isolated vertices, and then do complementation, you get a complete graph. And a graph which looks like this. Let's see if such a graph is actually a cograph. Now, complete graphs are cographs. So this K2 is cographs. We can add a bunch of isolated vertices using zero sums, and then you do complementation on this graph, and you get this. So this is another example of cograph. Okay, so we have this nice class of cographs, and the operations used are complementation and zero sums. What happens if we add another operation, that is the operation of one sums? We get another class of graphs, which we call two-cographs. And the first part of the talk will be about these graphs. So two-cographs are defined as graphs which are generated from K1 using complementation, zero sums, and one sums. Again, examples. What are examples of two-cographs? Well, of course, cographs, because you're adding one more operation to it. Let's see if this graph is a two-cograph. So what we allowed is zero sum, one sum, and complementation. And we start with the single vertex graph. So we know that K2, we can get that from single vertex graph. And in fact, in the last slide, we actually showed that complete graphs are cographs. So this is a two-cograph. We take 4 such copies of K2, one sum them together, we get this, and then take complement, we get this graph. So this is an example of a two-cograph. Now, as I mentioned before, there are lots and lots of ways of describing cographs. The one we started off with was the recursive definition. And here's an alternative definition in terms of induced subgraphs. And we say that a graph is a cograph if every connected induced subgraph you take has a disconnected complement. Or in other words, G is a cograph. You take an induced subgraph of G, H need not be proper, then H or H complement is disconnected. So another way of describing cographs. Now, the natural question is, does this definition generalize to two cographs? Okay, so in other words, can I go ahead and replace this G with two cograph and add connectivity, add two connectivity instead of connectivity here? And the answer is yes. So G is a two cograph if and only if every induced subgraph you pick, either the induced subgraph or its complement is not too connected. Okay, so that's an example. That's another definition of two cographs. Okay, any questions about the definitions? All right. Well, there is another way of describing cographs, and this is a characterization by Gordon Royal. This uses the operation of join. So let me describe what join of two graphs is. So if G and H are two graphs, we require them to be disjoint, and we define join of G and H to be, you take G, okay, hey, you have G, and you have a disjoint graph H, and you join every vertex of G to every vertex of H. And that's how you get join of two graphs. And by introducing this new operation join, we can actually remove the complementation operation from the recursive definition and have a definition in terms of zero sums and join operations. So cographs can be defined as graphs generated from single vertex graphs using zero sums and join operations. Again, can we generalize this to two cographs? And the answer is, again, yes. And for that, we need to kind of alter the join operation. So we call this new operation, which generalizes this join operation, alternating join. And what we're doing in this alternating join operation is we are just allowing, we no more require G and H to be disjoint, and we allow them to meet at most one vertex, okay? So in other words, I have my graph G and H, and they may meet at one vertex, and then I join all the non-common vertices of G to the vertices of H. Okay, so that's what this new operation, alternating join, is. And we get a recursive definition of two cographs in terms of zero sums, one sums, and alternating joins, or alternating join operations. Okay, so definitions. So there are some characterizations of cographs which generalize to two cographs as well. Okay, so enough with characterization. Here are a few quick observations. Now, cographs, the definition in terms of induced subgraph was every induced subgraph you pick for cograph, either H or H complement is disconnected. Both cannot be connected. And for two cographs, H and H complement both cannot be two connected. And that is true for all induced subgraphs. Now, this property is, preserved under induced subgraphs. So that means that the cographs and two cographs, the classes of these graphs, are closed under taking induced subgraphs and complementation. Another quick observation is all graphs on less than equals to 4 vertices are two cographs. And this is straightforward because you cannot have a graph on at most 4 vertices where both the graph and its complement is two connected. So that means, you cannot have an induced subgraph such that both the induced subgraph and its complement are two connected. So that clearly implies that the graph is a two cograph. Okay. All right. So now one might ask, how do we identify these two cographs? Is there a way that we can identify these two cographs? So let's start with this graph and see if we can have an algorithm which identifies this graph. So first of all, the thing which we can do is we can check the number of vertices of the graph. If the number of vertices of the graph is at most 4, then G is a two cograph. Okay. And if not, then what we do is we look at G and G complement. Either one of them is not two connected. Because if both are, then you got an induced subgraph such that both the induced subgraph and its complement is two connected, so not a two cograph. So either one of them is not two connected. And then what you do is find the block decomposition of the one which is not two connected and repeat this process for every block. So in our case, we had this G. G doesn't have, at most, G has 5 vertices. So we go to the second step. G is two connected. So we look at its complement. Its complement is just a path. And that is not two connected. So we find the block decomposition of that, which is nothing but 4 copies of K2. And K2, we already established, is a two cograph. So that means, this graph is a two cograph. Okay. All right. Now, another question, example of two cographs, but not cographs. Now let's look at this graph. What about this graph? This graph is self-complementary, is connected. So can this be a cograph? Okay, so cograph cannot have induced subgraphs such that the induced subgraph and its complement both are connected. But this graph and its complement is connected. So this is not a cograph, but this is a two-cograph because graph on less than equals to 4 vertices. Okay, so this is an example of a two-cograph, which is not a cograph. Okay, so this is special in the sense that we can actually characterize cographs in terms of this forbidden graph. In other words, we can say that G is a cograph if and only if G has no induced path of length 3. Now, a natural question to ask is, do we have such a nice list for two cographs? Can we say something like that, that G is a two-cograph if and only if G has some forbidden structures we can come up with? The first thing we would look at is induced subgraph minimal non-two cographs. Or in other words, the graphs G such that G is not a two-cograph, but every proper induced subgraph is. So, and we want to see, we wanted to check if such graphs have a very nice description, and we were not actually able to find a very nice description of such graphs. We found out that there are infinitely many, and example of one such infinite families is cycles of length bigger than equals to 5. So let's try to see how cycles fit in this family. Okay, so cycles of length bigger than equals to 5. Are they two cographs? Well, if you take cycle of length bigger than 4, that cycle is two connected and the complement is also two connected. So you have got an induced subgraph which is two connected and the complement is also two connected. So that is not a two cograph. Okay, now proper induced subgraph of cycles. When you remove a vertex from from a cycle, you get a subgraph of a path. So that is a two cograph. So this family is indeed in here, and there's no very nice description of the other families which we found. So okay, so what do we do next? It turns out that we already know two cographs are closed under induced subgraphs and complementation. It turns out that they are closed under contractions as well. So now we can talk about induced minors. And in other words, we can try to find graphs G, which are not two cographs, but every proper induced minor is a two cograph. Again, we did not find a very nice description. And complements of cycles of length bigger than equals to 5 is a family which is in this class. So now the question is, how do we find a nice result? And remember, this class of two cographs is closed under complementation. So we brought complementation into picture and got this result. Okay, so G is a two cograph if and only if none of the graphs in a finite list L, which we found, can be obtained from G by taking induced minors or complementation. Okay, so what are the graphs in this finite list L? This finite list L has graphs G such that both G and G complement are induced minor minimal non-two cographs. So now, in the rest of the cographs, two cograph part, we will try to see how we can get this L finite, this list L finite. And remember, this list L has graphs G such that both G and G complement are induced minor minimal non-two cographs. Induced minor minimal non-two cographs? Well, G is not a two cograph, but every proper induced minor is a two-cograph. Okay. Now, examples of graph in this list L. And this is, graphs in L are the graphs such that both G and G complement are induced minor minimum. Now let's look at this 5 cycle. Is this 5 cycle in L? So first of all, this 5 cycle is self-complementary. So we do not have to worry about the complement, and we just need to check if this 5 cycle is induced minor minimum. So first thing for induced minor minimal we check is this should not be a two-cograph. And the answer is, yeah, it is not a two-cograph because 5 cycle is two connected, and the complement is again a 5 cycle, which is two connected. And you cannot have that in two-cographs. You cannot have an induced subgraph, which is two connected, and the complement also two connected. So this is not a two-cograph. And when you delete vertices or contract edges to get a proper induced minor, you get a graph on less than equals to 4 vertices, which means a two-cograph. Okay, so this is a graph in L. Another example of graphs in L is a complementary pair of graphs, the 6 cycle with a chord and its complement. The red graph is the red graph. We use this red color to denote the complement of this. Now, both these red and green graphs are induced minor minimal, which means that when you delete vertices or contract green or red edges, you destroy the two connectivity of red or green graph. And now what we want to show is that if you take any graph in this list L, the number of vertices of such graph is bounded above by 10. Okay, so you have this graph in L. Now, as soon as you delete a vertex, you get an induced minor, a proper induced minor, and you cannot have both red and green two connected because it's proper induced minor. So when you delete a vertex, you reduce the connectivity of red or green graph. Now, it might happen when you keep removing every vertex you remove, you actually destroy connectivity of just the green graph. In that case, well, G is critically two connected. And we find that in that case, we have G a unique graph, which is this, okay? Or the other case is you keep deleting vertices. Sometimes you disconnect or destroy the two connectivity of red graph and sometimes the green graph. In that case, vertex connectivity is two. So that's the case left to tackle. And the idea is this. Okay, connectivity of the green graph and the red graph is two. So there is a two cut. And let G1, G2 be such a two cut. Okay, so that's a two cut. And you arrange the components, combine the components into A and B such that the smallest component has at least two vertices. Okay, so that's a condition I'm imposing that you somehow combine the components such that the smallest component has at least two. And now if you look at this, all the edges going from A to B would be red, right? Because if G1, G2 is a cut of a graph, that means the vertices in A and B are not adjacent, which means that they're adjacent in the complementary graph, which means red graph. So red, if you can see from here, it's highly connected, this thing, and these vertices G1, G2 have kind of latched onto this highly connected graph using the red edges that they have. Now, if I can find a contractible green edge, meaning the contractible edge of the original graph, or by contractible, I mean I contract this and do not affect the two connectivity of the green graph. So if I can find such an edge here, then the two connectivity of the red graph is also not affected, okay? So that's the idea. So provided we can find, provided B is bigger than equals to 2, we can find a contractible edge, E here, and that gives us a win. So the only thing is what happens in case B is 1. So if B is 1, then there is a single vertex here, and that has got degree 2. And that happens both for the red graph and the green graph. So we know from this illustration that the problematic vertices here are red degree 2 vertices and green degree 2 vertices. Okay, so what do? We do some case analysis on this thing and some analysis on these red degree 2 vertices and green degree 2 vertices bounds the number of vertices in our graph. And that gives us the result. Okay. So we get our final result by doing some analysis on these red degree 2 and green degree 2 vertices. And once we have this bound, we use Sage to find explicitly the graphs we were looking for. So when the number of vertices is 5, we get a unique graph, and that graph is, well, we just gave the example, which is the 5 cycle on 6, that complementary pair, and so on 7, 8, 9, and 10 vertices. Okay, so that was the part of about two-cographs. Any questions about this two-cograph stuff? We'll move to matroid stuff now.
Yes, I'm actually a bit confused about the contraction in two-cographs, like why that keeps a two-cograph.
Yes, so the idea is, well, we can prove that by contradiction. If you have a two-cograph, and let's say the contraction is not a two-cograph, then what would happen is that there exists an induced subgraph of G contract E such that the induced subgraph of G contract E is two connected and the complement is also two connected, right? Does that make sense? And we can use this induced subgraph of G contract E to get an induced subgraph of G, which is two connected and the complement is also two connected. So, you know, we kind of move.
Well, that's what I don't see. So, I mean, so contraction in the complement is just identifying a non-adjacent pair. So you could have a cut vertex in the complement, but then I am identifying a pair of vertices on either side that destroy the cut vertex.
I'm not sure I completely understood your question.
If I have a cut vertex in the complement,
you can't have a cut vertex in the complement because the complement is two connected.
no, I have a graph that's not. I have a graph that's a two-cograph, and I'm contracting an edge in it. And the reason, and one of the reasons, like in the decomposition, why it's a two-cograph is that in the complement, say it's got a cut vertex. So that's like part of the decomposition. But now I take a vertex on opposite sides of that cut vertex and I identify them, and I suppose I don't have any cut vertices anymore. Like,
okay. Maybe we can talk about this.
okay, we can
use the matroid.
Sure, we can move on. I just don't see it.
Okay. All right, so let's move to matroids. Now, cographs were defined as the graphs which were generated from single vertex graphs by zero sums and complementation. Now, how do we find matroid analog of that? K1, well, how do you find? Now, when I'm saying matroids here, I'm just dealing with binary matroids here. So when I say comatroid, I mean binary comatroid. So cographs generated from K1 using complementation and direct sums. So we find the matroid analog of that. That is, we consider the binary matroids generated from the empty matroid by direct sums and complementation. Now, when I'm saying complementation, I mean you can embed the matroid in a higher rank projective geometry and then take its complement. Okay. So it need not be, the projective geometry need not have the same rank as the underlying matroid. So we define this class of binary matroids, and we call that class comatroid. So examples. One obvious example is projective geometries and free matroids. How do we get projective geometries? Well, take the empty matroid and embed it in a projective geometry you like, and take its complement. So you get a projective geometry, and U11 is a projective geometry. Take as many direct sums of U11, you get the free matroid. Another example is affine geometry. how do we get affine geometries? Well, take a projective geometry and embed it in a projective geometry of one rank higher, and then take the complement, and that would give you the affine geometry, okay? So these are some obvious examples of binary comatroids. And remember, for cographs and two-cographs, we had a description in terms of induced subgraphs. That is, for cographs, we had this description saying, you cannot have an induced subgraph which is connected and the complement is also connected. That was for cographs. And for two-cographs, we had, you cannot have an induced subgraph which is two connected and the complement is also two connected. Now for matroids, induced subgraph would kind of correspond to flats. So an analog of that holds for comatroids as well. That is, if you take a connected flat of a comatroid and you consider its complement, the complement is either disconnected or has rank less than the rank of the flat, okay? And this enables us to see that comatroids are actually closed under taking flats. So in other words, every flat of a comatroid is a comatroid. And of course, complementation. So closure under flats and complementation. Now, this thing, which I just mentioned here, we can spend some time trying to understand or visualize what's going on. So comatroids, as I understood, as sometimes I would have that picture in my head, is comatroids can be thought as two coloring of the binary projective geometry. So color the elements of the binary projective geometry green and red. And of course, we're talking about binary projective geometry, so rank bigger than or equal to 4. Now, when you two color a projective geometry, you cannot have both disconnected, right? So either the red or the green is connected of rank R, full rank, right? So either one of them. Actually, we proved something stronger than that, but let me not get into that. So either one of them is connected, but for comatroids, exactly one will be connected of full rank, right? And why is that? Because if both of them are connected of full rank, then we have got a connected flat whose complement is also connected and full rank. So we cannot have that for comatroids, okay? Any questions about this? So in other words, when you two color a binary projective geometry and we say that this two coloring is comatroid, then every flat is either red connected or green connected, or in other words, we can say every flat is kind of, every projective flat is kind of red or green, okay? And we had this result for cographs in terms of this forbidden structure that is path of length 3. And we said that G is a cograph if and only if G has no induced path of length 3. Now the question is again, do we have something similar for binary comatroids? Can we have, do we have a result which is like M is a binary comatroid if and only if M has no flats in a well-described list? And the answer is yes. So this is the main result, which says that M is a binary comatroid if and only if M or M complement has no flat isomorphic to a circuit of size bigger than 5 or cycle matroids of the following 7 graphs. Now these matroids, these forbidden matroids, which I just described or said, these are actually induced restriction minimal non-comatroids. So the problem was to find those non-comatroids such that every proper flat is a comatroid. Okay, so that was the problem which we tried to answer. We're looking for such matroids whose every proper flat is a comatroid, but the matroid itself is not a comatroid. Now, this list of matroids is closed under complementation. And examples. What are the examples? Now, if you look at circuits, circuits of size bigger than 5, as we already talked about, are not comatroids because circuits are too connected. Well, of course, size bigger than equals to 5. Circuits are too connected, and the complement is also too connected. So you cannot have that for comatroids. But if you look at a proper flat of a circuit, that's a free matroid. And free matroids are comatroids. So circuits are example. And since this list is closed under complementation, the complements are also in there. And it turns out there are not many examples apart from this, as we mentioned in the previous slide. So how did we prove this? We made use of this result of about connected hyperplanes in binary matroids by McNulty and Wu, which states that if M is a simple connected binary matroid and has no co-circuits of size less than 3, then every element is in at least 2 connected hyperplanes, and M has at least 4 connected hyperplanes in total. Okay, so every element is in at least 2 connected hyperplanes. Okay, so let's look at the idea of finding this induced restriction minimal non-comatroids. Again, we have this matroid M, which is induced restriction minimal, and we think of this being embedded in the same rank projective geometry. And look at a proper flat of this projective geometry. This proper flat is supposed to be a comatroid, which means both red and the green cannot be too connected at the same time. So either one of them is too connected. So either the red points of the flat, of the projective flat F, that is connected, or the green points of the flat F are connected or full rank. So we call the flat green and red depending on which one is connected or full rank. Okay, so we consider all the hyperplanes. Now hyperplanes are divided between green hyperplanes and red hyperplanes, and similarly for rank R-2 flats. So we have these 4 subsets. This is all the hyperplanes, and some hyperplanes will be green, some hyperplanes will be red, and some rank R-2 flats will be green, and some rank R-2 flats will be red. And now what we do is we make a bipartite graph of it, with one partition being this side and the other side being this. And how do we define edges? Well, by inclusion. So xy is an edge if x is contained in y. And the idea is we count the cross edges, that is G1R2 edges and G2R1 edges. So we count these cross edges, and we count them in 2 different ways. And we count them in 2 different ways, and that gives us this inequality. And if we fiddle around with this inequality, that gives a bound on either G1 or R1. So what is G1 cardinality? Well, the size of G1 is nothing but the connected hyperplanes of M, and R1 is the the red hyperplanes, which means these are the connected hyperplanes of M complement. So fiddling around with this inequality gives us this, that either matroid M or M complement has less than 4 connected hyperplanes. But McNulty and Wu's result said it has at least 4 connected hyperplanes, provided the matroid is co-simple. So that means a matroid M or M complement has a 2-core circuit. And then we show that if M has a 2-core circuit, then M is either circuit or this. And how do we show that? Well, if M has a 2-core circuit, M looks like this. And the next observation that we made is that M2 has no connected hyperplane containing P. Because if M2 has a connected hyperplane which contains P, then M has a proper flat M has a proper flat which is connected and has a two-core circuit. And if you look at the complement of that flat, that is also going to be two connected because it contains an affine geometry minus 2 points, right? Because of the two-core circuit. So then you get a flat which is connected and the complement is also connected. So that's a contradiction. So you cannot have that. So that's why M has no connected hyperplanes containing P. And by McNulty and Wu's result again, that means that M2 is not cosimple and it has a two-core circuit. Now we keep on repeating this process and that gives us our result. Okay. Now, the next question is, well, we did the same thing for ternary. We did define comatroids for ternary matroids as well. And all we did was we replaced binary by binary projective geometries with ternary. And again, the problem was the same. We wanted to find all induced restriction minimal ternary non-comatroids. Now, as the illustration for binary comatroids shows, that we needed a result like McNulty and Wu's to have a bound on the number of connected hyperplanes. We did not have that for ternary matroids. So we tried proving something like that, and we actually did end up proving a result for ternary matroids, provided we have a bound on the number of co-circuits. So we do not allow co-circuits of size 1, 2, and 3. And provided we have that, we are guaranteed that M has at least 2 connected hyperplanes. And well, we do not know if this is optimal, but for our purpose, we actually needed just 1. So 2 is good enough. And now the question was, can we find induced restriction minimal ternary non-comatroids? Circuits again are examples. And not just circuits, but if you take a circuit and on some of the elements of the circuit, you do some copies of U24, that also is an example. And it turns out that there are not many other than these. So this is the result, which is M is a ternary comatroid if and only if M or M complement has no flat isomorphic to either circuits or circuits with U24 summed on it, 2 summed on it, and matroids in this 5-element set. Okay, so that was the result which we proved for ternary comatroids. So I'll stop here. Thank you for listening.
Hey, thank you, Jagdeep. Let's do a round of applause. So if everyone can unmute, and then I'll count to 3, and then we'll clap. 1, 2, 3. Excellent. Okay, and does anyone have any questions, or maybe do we want to go back to the earlier question?
I'll ask a question, Jagdeep. So when did cographs arise, and why were people interested in them to start with?
Cographs?
Yeah. So when did people start investigating them, and why?
Well, I mean, cographs is a natural class if you look at it. Well, recursively they are generated like that, and yeah, I mean, it has been widely studied. I think it's very natural. Yeah, go ahead. Sorry.
I mean, were people looking at them 20 years ago or before that? Or I'm just curious to know. I mean, you had some results from cographs, but I presume they weren't yours. But you didn't state who they were by or anything like that.
Oh, yes. I mean, lots and lots of work has been done on cographs. People have been interested in this over the last 50 years, I would say. And the result about
the 4-path or whatever,
which I stated about,
whatever.
Yeah, that result was of Cornell.
Okay.
And people have been interested in algorithms to identify them. And yeah, I mean, I was looking at different references for this, and there's lots done on regarding cographs. So, and I think it started off like 50 years ago.
Thanks. It was a nice talk.
Thanks.
Any other questions? Or maybe shall I end the recording there and then we can discuss more afterwards? Last chance? Okay, I'll stop the recording there.